In my first lecture, I have explained the introduction only in chemical kinetics, and it was just the preliminary discussion on the chemical kinetics. Now today I shall be going to discuss more important part of this chemical kinetics, which is the rate law, and hence the order of this reaction. Before that, I like to say you all that this lecture not only useful for the chemistry honors students, but at the same time it will be much helpful for the students aspiring IIT-JEE and also NET, GATE and IIT-JAM examinations. So before going to explain the rate law and order of chemical reactions, I like to say what are the factors on which the rate of this reaction depends. First of all, one first factor on which the rate of this reaction depends is the nature of the reactants and nature of the reactants. And you know, we have nothing to do with this nature of the study of this nature of this reactants. Chemical reaction is nothing but the breaking of the old bonds and making of the new bonds. This is the chemical reaction. And we are discussing only the molecular reactions where some bonds are breaking and new bonds are being formed during this chemical reaction. So it is a molecular reaction. So we shall not discuss the ionic reactions. And now how the chemical bond is broken up and new bonds are being formed while these reactants are going on chemical reactions, it depends on the nature of these reactants. Next, the dependency factor is concentration of a reactant or effective mass of this reactant. Or you can say more broadly, in some cases it is found that the rate depends on all the reacting components, means reactants and products also coming in the picture of this dependency of this reaction rate. So this is a very important portion and preliminary guidance or the main format of the dependence of rate of a reaction on the concentration of the reacting components was given by Gould and Wajay in mass action law. Now the idea of this Gould and Wajay is much more modified, and actually in that case, say stoichiometric coefficients of the reactants and products are much more important in case of this illustrating the mass action law. But in our case, the rate law is formed rate law is written on the basis of this experimental fact. It is the experimental entity, not the stoichiometric equations, and stoichiometric equations are nothing to do with the formation of this rate equation. Means how the rate of this reaction depends on the concentration of the reacting components. It is totally the experimental quantity. And the third one, very important dependency factor, which is the temperature. And you know already, with increase of temperature, any process, rate of any process is increased, enhanced. Even if you are washing some clothes with this detergent powder, if you use this hot water, then cleaning will be more better and more faster. You know, say process of aging, biological process of aging, biological process. In hot countries like India, Bangladesh, Pakistan, etc., etc., people looks old relatively at the age of 60 or 65, like that, as the rate of the aging process much more accelerated at this high temperature. While if you see the people in cold countries, the temperature is low and the rate of this aging process is also slow. So people there at the age of 60, 65 looks more young than us, which are living in hot countries. Again, there are so many illustrations I can give which are of very practical use. So whenever a milk you keep in a freeze at a temperature of 5 degrees centigrade, it takes 1 week long to get it sour, to get it destroyed. But if you keep the same milk at this room temperature at a temperature of 30 degrees centigrade, within 7 or 8 hours, it will be destroyed. Their rate of souring at low temperature is very low, while the rate of souring process of this milk is very high at this high temperature. So this is illustrated in Arrhenius equation. Whenever we shall study the Arrhenius equation, we shall discuss very illustratively with some problems also how the temperature can affect the rate of this reaction. And the fourth one, the rate of a reaction depends on the presence of some foreign substance. Foreign substance, it is not that it is imported from the foreign countries. It is neither the reactants nor the products. Simply, it remains unchanged in mass and composition. But the presence of this that foreign substance, which we can call catalyst, increases the rate many times. Suppose decomposition of hydrogen peroxide to water and oxygen. it goes very slowly at room temperature. But at the same room temperature, if you add some platinum catalyst, platinum powder, the rate is highly enhanced, rate is highly increased. So this is the role of catalyst. Now, the research on catalyst on different reactions getting high momentum. Nowadays, the enzyme catalyst is coming up, which requires a very, very small amount, which can increase this rate many fold. Then again, in case of heterogeneous catalyzed reactions, that means reactants and catalysts are in a different phase. In that case, a degree of fineness of this catalyst increases the rate of this heterogeneous catalyzed reaction much more. Greater the degree of fineness of this catalyst, higher will be the rate of this reaction. And last dependency is the light, if falls on this reacting vessels, reacting components. And you know, the many reactions occurs only by the absorption of light of suitable wavelength. They do not occur in dark. Many reactions are there. They are called photochemical reactions. So hydrogen and chlorine kept in a vessel, in a room, in a dark room, the reaction occurs so slowly that there is no such noticeable change after a long time. But if that hydrogen and chlorine, these reactants exposed in sunlight, reaction occurs very quickly, very rapidly, and HCl is being formed. One common example I can cite the photosynthesis of carbohydrate that occurs in tree leaves in the presence of sunlight, and carbon and water, they are the reactants combined in presence of sunlight, catalyzed by the chlorophyll. Chlorophyll absorbs this light, transfers to the reactants, and the carbohydrate are being formed. So this photosynthesis of carbohydrate is the very important reactions on which the human beings or say any animal world can live. We eat the carbohydrates, vegetables, or we eat some animals also which are dependent on the consumptions of the carbohydrate. So this photosynthesis is a prime reaction on which all animal world live or can survive. Now, I am going to discuss the rate law. Rate law means it is the equation, sometimes also called the rate equation, which is the statement how how the rate of a reaction depends on the concentration of these reacting components. And it is, as I said before, it is totally the experimental entity. Say, one example I can cite here, say hydrogen peroxide undergoes the decomposition, say in presence of this platinum catalyst, or in presence of this ferric ions, or in presence of some enzymes. It gives water plus it is 2, it is oxygen. Oxygen is liberated. This reaction I have already mentioned before in my first lecture. So, how the rate of this reaction depends on the concentration of hydrogen peroxide at a given temperature with a given catalyst. So, rate of this reaction which we can simply write R, rate of a reaction The reaction, which is the reaction? Reaction is the decomposition of hydrogen peroxide in presence of catalyst at room temperature. Experimentally, it is found that it is proportional to the concentration of hydrogen peroxide and single power. Though the coefficient here is stoichiometric coefficient is given in the equation 2, chemical equation 2, but the power is 1. How could you know what will be the power? This could be done from the direct experiments. As the concentration of hydrogen peroxide is doubled, rate of this reaction, rate of decomposition of hydrogen peroxide is also doubled. Means this rate is directly proportional to hydrogen peroxide. We have nothing to do with this stoichiometric equation, stoichiometric coefficients. It is only obtained by experiment. It is only you can know from this experiment at a given temperature with catalyst. Say this one indicates the order of this reaction. Order of this reaction. Say another example I can cite here. Suppose nitrogen pentoxide. Nitrogen peroxide, nitrogen pentoxide decomposes 4NO2 plus oxygen. And you know this rate equal to minus half D N2O5 divided by dt equal to or proportional to the concentration of N2O5 to the power 1 only. So this is first order reaction. This is also first order reaction. Though the stoichiometric coefficient here I have written 2, but the power experiment shows that the rate of the reaction becomes double when the concentration of nitrogen pentoxide gets doubled. Another reaction say hydrogen gas plus iodine gas twice HI. So rate of this reaction, either you can write in this rate, you can write either in terms of this hydrogen or in terms of this iodine or in terms of this HI. This rate will be proportional to concentration of hydrogen single bond and concentration of iodine single bond. In this case, we are lucky to see that the powers happens to be equal to the stoichiometric coefficients for this reaction. These are all molecular reactions. These are all molecular reactions, not the ionic reactions. So whenever you replace this proportionality, there will be some constant K. In this case also, say decomposition of hydrogen peroxide minus the concentration of hydrogen peroxide divided by dt, where half you can write equal to K into concentration of hydrogen peroxide to the power 1. K is the rate constant. K is rate constant for a reaction, and it remains all along constant if the experimental conditions are not widely varied. So this K is rate constant. You can define this rate constant in more illustrative way. If you keep the concentration of hydrogen peroxide 1 mole per liter initially, then the initial rate will be equal to K. Or whenever the concentration of hydrogen peroxide is equal to 1 mole per liter, the rate of this reaction is equal to K at that concentration. So this K is sometimes also called, it is called rate constant, or it is also sometimes called specific reaction rate. Specific reaction rate. Specific means whenever one unit is taken. Specific volume per gram of the substance. Specific heat required for a substance to for 1 gram substance by 1 degree. And so specific term is used, specific reaction rate sometimes used for the rate constant of this reaction. It is a constant at a given temperature for this reaction so long experimental conditions are not widely varied. And the power, you know, this power of this concentration on which the rate depends will decide the dependency of the concentration of the reacting components on this rate of this reaction. One general type I can show you. Say twice A plus B and giving you C. A and B are the reactants, C is the product, and the rate is found to be equal to some constant, and concentration of A to the power 1 and concentration of B to the power 1 also. Or you can write concentration of A to the power X, concentration of B to the power Y. X and Y, these are the exponents, these are the powers on which the concentration affect the rate of this reaction. X and Y may be any number. X and Y, X, Y, maybe 0. Suppose X is 0, means the rate does not depend on the concentration of A. That means the rate is a 0 order with respect to A. Say B equal to 1, means the rate depends directly proportional to the concentration of B. Keeping A fixed, if you double the concentration of B, the rate will also be doubled. So it is the single power Y equal to Y equal to 1. Here X equal to say 0. X may be 0. So this X and Y may be any number, 0, 1, 2, 3, -1, negative, even negative, fraction. And this we can know only from this direct experiments. Direct experiment. Nothing to do with these stoichiometric equations. So if the power, say X equal to X and Y, sum of the two coefficients, the sum of the two exponents, powers, equal to n, and n called order of this reaction. Order of the reaction. So order n of this reaction will be of any number including 0, negative, fraction, etc. So one example I can show you, the decomposition of acetaldehyde. Decomposition of acetaldehyde at a certain temperature, say 450 degrees centigrade, it gives you 8 methane plus carbon monoxide. And this rate equal to minus, say, the CH3CHO divided by dt, differential rate, differential form of this rate at a given instant. And this is equal to some constant, and concentration of CH3CHO to the power 3/2. It means that the constant, if you increase this concentration double with the power 3/2, means 1.5. If you increase this concentration, the rate will also increase by 1.5 times. So this is the fractional order 3/2, and this can only be known from this experiment. This can only be known from this experiment, and not with this stoichiometric coefficient of this balanced chemical equation. So order may be 0, 1, 2, 3. Order means A. Negative, fraction, etc. But order may not be or must not be greater than 3. Whenever we shall study the mechanism of chemical reactions, we shall see the reactions more than third order, or order of this reaction rarely third order, and more than third order is impossible. For the third order reactions, 3 species must strike simultaneously to form the product, and 3 molecules or 3 species collide simultaneously. It is highly improbable or least probable. And more than 3 molecules colliding at the same time, it is impossible. So it is maximum third order. One example I can show you: twice NO plus chlorine and giving you twice NO Cl, and the rate, say, minus the concentration of Cl2 divided by dt equal to some constant K, and concentration of NO to the power 2 and concentration of this chlorine to the power 1. So this N equal to x plus y, and it is equal to 2 plus 1 equal to 3. Here also happens this stoichiometric coefficient becomes equal to the power of the concentration terms. This is a very rare case. So it is third order reaction. So the reactions very conveniently grouped on the basis of the orders. Some reactions are 0 order, some reactions are first order, some reactions are second order, some reactions are third order, and so on. Most common reactions are first order and second order. Of course, each and every reaction could not be identified with this order of this reaction. It is not possible in all the cases. And you know, the 0 order reactions have certain characteristics, first order reactions have certain characteristics, second order and also having certain characteristics, and so on. But one example I can show you in which you cannot decide what will be the order of this reaction. Say one very simple reaction goes very complicated way. Say hydrogen gas plus bromine gas, and giving you twice HBr, and it is also gas. This reaction looks very simple, but goes very complicated way. Complex reactions. Only limited reactions or elementary reactions means occurs in a single step. Most of the reactions are complex reactions, goes in a series of steps. Whenever we shall study this reaction, I show you the mechanism. Or the mechanism means a detailed description of the paths through which the reactants comes over to the product. So this will go in several steps, and the rate of this reaction or the rate law or rate equation, whichever you may call, very complicated. And one scientist, Bodenstein, in 1919 proposed a certain mechanism on the basis of which the rate of this rate equation is being framed. And the rate equation is formulated like this way: half d HBr by dt equal to some constant K, concentration of hydrogen, and concentration of Br2 to the power 3 by 2 and to the power half, divided by 1 plus another constant K dash, concentration of HBr divided by concentration of Br2. So this rate equation is very complicated, and from this rate equation you could not predict or specify what will be the order of this reaction. And very surprisingly, you can see the product of this reaction also enters in this rate equation. And this is why I have told you that not only the reactants but the products also may also involve in this rate equation. So in general, we can call the reacting components. Concentration of reacting components will decide the rate of this equation and rate of this reaction, and this is called the rate law. Only at this initial stage, say initial rate, if you study the initial rate means of starting point, whenever this hydrogen and bromine are mixed up at a given temperature, and just initially if we study the rate of this reaction, then reaction initial rate will be initially HBr forms a very, very small quantity and bromine present in large amount. So the concentration of HBr and divided by concentration of Br2 much less than 1. This is very large amount, this is very small amount, this is very large amount, and this ratio becomes very, very small in comparison to 1, and this denominator, second term in this denominator, you can neglect. So in that case, this rate, say initial rate, you can write R0, 0 means at 0 time, and this will be equal to some K and concentration of hydrogen and concentration of Br2 to the power half. So this N order of this reaction is 1 plus a half, and this is the 3 by 2. So initially, if we study the rate equation, if we at this initially you can write this rate equation like this, and it becomes this third order. So actually this is why I have told the initial rate of this reaction sometimes becomes more important than in later stage of this reaction. Complications are minimized. As the vessel contains large concentration of these reactants and almost no products or very small amount of the products. So this is all about the rate law, and I say something about this rate constant. Say, very simple, the hydrogen constant. I am giving you water plus oxygen, very common reaction. And rate is equal to some constant concentration of hydrogen peroxide to the power 1. First order reaction. It is the first order reaction. So this unit of K, what is the meaning of this K rate constant? Rate constant is the rate of this reaction when the concentration of hydrogen peroxide have been taken 1 mole per liter. Say for nth order reactions, A to P, and it is nth order reactions. Nth order reaction. So in this case, this rate or minus dA by dt equal to some constant into concentration of A to the power A. Nth order reactions. So power of concentration term will be A. So what will be the unit of this rate constant? Unit of rate constant, unit of K equal to, say here it is concentration, say minus d concentration divided by concentration of A to the power A into 1 by dt. This is one. So this one is mole, this one is mole liter inverse, and here it is also mole liter inverse to the power n into 1 by time, and time suppose second, either second, minute, hour, etc. Smallest unit is second. So what will be the unit of this K? Mole 1 minus n liter mole 1 minus n liter minus n, whenever it goes to the numerator n, so n minus 1 and second to the power minus 1. Mole 1 minus n, liter n minus 1 and second inverse. here it is a mole, here it is mole to the power n, it goes upside minus n, so 1 minus n. Here whenever this L minus n goes upside, then it will be n, and here minus 1, n minus 1, and second inverse 1. Sometimes this unit of this rate constant is very much helpful to determine this order of this reaction. This unit is much helpful in many cases to determine the order of this reaction. Suppose the rate constant of a reaction is equal to 3.5 into 10 to the power minus 5 mole inverse liter and second inverse. What will be order of the reaction So you can take it nth order. So mole minus 1, here mole 1 minus n. So minus 1 equal to 1 minus n, or n equal to 1 plus 1 equal to 2, and this reaction is second order reactions. If the unit of rate constant is found to be only second inverse, means only second inverse, and this, in this case, it is 1 minus n equal to 0. 1 minus n equal to 0. So n equal to 1. So it is first order reaction. In case of first order reaction, the unit of K is always time inverse, second inverse. No concentration terms are included in this unit of rate constant. So this is all about the rate law and order of this reaction. And order of this reaction is determined only by experiment. As I have said, if it is found the rate of this reaction is doubled with the doubling the concentration of this hydrogen peroxide, then it is the first order reaction, directly proportional. In some classes, next classes, I will show you how to determine order of a reaction by different methods.